Hi, I'm Ms. Fung. Let's have a look at conditions for differentiability. When is a function differentiable? When can you find a derivative of a function? Well, let's have a look at a certain point, because most of the graph is differentiable, but we have to question whether this point here, x equals 0, is differentiable. So let's have a look. Here we have the hybrid line -1 and 1. Because of this big gap here, we don't know what the gradient there is. So we don't know the gradient there, so we say we can't differentiate it at x equals 0. So when we draw the gradient function or f dash x function, we can see that we can draw the gradient here 0, 0, but we have to draw a little hole where x is 0 because we don't know what the gradient there is. What about this one? Well, the gradient here, according to 2x plus 1, is just 2 on the left side, and the gradient to the right is going to be the derivative of that part of the equation, so 2x plus 2. Now the gradient at that point there where it joins from the left and right is both 2. We can see that it's quite smooth. So at that point we actually have a joint point. So yes, there is a derivative at x equals 0. What about this one? Here we have the gradient on the left side, 2x plus 2 is 2. See, the gradient here is at 2. Whereas the gradient on the right side, minus 2x plus 2, is minus 2. So the gradient is 2 on that side and minus 2 on the other side. And we see that at x equals 0, at that point, we have no gradient. It's in between those two lines. So yes, there's a gradient. Sorry, so no, there is no gradient at x equals 0 for that one. Yes, there's a gradient at x equals 0. And no, there's no gradient at x equals 0 over there. So what about this graph that makes that one have a gradient at x equals 0? Well, the formal statement is at that point, the limit of h approaching 0 of f of 0 plus h minus f of 0 over h does exist. That is the formal definition. Whereas here and here, that would not work. So the formal definition, a function f is said to be differentiable at x equals a, so the value like before was 0, if the limit of h approaches 0 of f of a plus h minus f of a over h exists. But visually, how do we check? We only have to check two things, whether it's continuous or smooth. So remember here, it's not continuous, so no derivative. Here, it's continuous but not smooth at that point. See, it's pretty sharp, so it's not differentiable. Whereas here, it's continuous and it's smooth, so definitely differentiable. So these functions are differentiable for all real values except for at x equals 0. This is differentiable for all real values, and again this one is differentiable for all real values except for x equals 0. Or in other words, f dash x is defined for all real values except for x equals 0 for this one and this one, and f dash x is defined for all real values for this graph in the middle. What about these ones? You give these a go, pause the video and unpause to see if your answers match mine. So determine if the function is continuous, differentiable, both or neither at the special point. At 3, is it differentiable? Definitely not, because it's not even continuous. At 1, the limit exists, but there's a hole there, so it's not continuous. And if it's not continuous, then you can't differentiate it. At x equals 0, we can see that the graph continues, and therefore it's smooth as well, and therefore it's differentiable. For graph D at x equals 0, we can see that it is continuous, but it is not smooth, so you cannot differentiate it. For this one, it's pretty obvious that there is no, it's not continuous. So if it's not continuous, then you can't differentiate it. So remember, you have to check if it's continuous, it could be differentiable, but it has to be smooth, not sharp. What about this one? So again, yes, continuous at x equals 0. but not differentiable because it's not smooth. What about this one? At x equals 2. Yes, it is continuous, but it's not differentiable because it's not smooth. This one is a trick question. You're going to see it next year, but I thought I'd put it there just for fun. You don't need to know it. That one there looks like it is differentiable because it's smooth, but it's actually not, because if you look at the gradient at x equals -1, it's actually undefined because it's vertical. So that's a special case, but you won't see until next year, so don't bother. But if you wanted to see when it is smooth but not differentiable, that's the only time, when it's vertical. But I'm going to only give you examples where it's smooth and does have a derivative. I won't give you an undefined derivative. So to recap, check that it's not sharp, check that it's smooth and continuous, then you say differentiable. Example 2, show that the following function is differentiable at x equals 1. So x equals 1 is the point where the two lines meet. So from the left side, we're looking at 2x plus 8, and from the right side, we have x squared plus 9. Now, do you remember limits? How do you show whether a limit exists? You say the left limit, the right limit. If they're equal, the limit exists. If they're not equal, the limit doesn't exist. Differentiation is the same. You try to differentiate from the left, differentiate from the right. If the numbers match, then you can differentiate it at that point. If they don't match, then you can't differentiate it at that point. So let's do the left side. And remember, the left side, you do it by just showing a little negative, so x negative. So from the left side, we have the equation there. When you differentiate it, you get just 2. On the right side, when you differentiate it, you get 2x. So when you sub in x equals 1, because that's what we're talking about, from the left, see the -1, we have, well, when you sub in, there's no x there, so you can't put 1 anywhere, so 2 just stays as 2. But from the right side, when you sub in 1, you get 2 times 1 is 2. So the left equals the right, so therefore the function is differentiable at 1. See, left, right, yes. First derive the both sides, then plug in the number. Then tell me whether it's the same or not. What does the graph look like? So from the left side, 2x plus 8, it looks like this. And at this point, both sides have a gradient of 2, so it's a smooth joint. If the gradients were different, then it wouldn't be smooth. Example 4, for the following function, state the set of values for which the derivative is defined. Well, we only have to check at the gap. Can you differentiate it at x equals 3? So again, we do the left side. So left side, bring the 2 down. 2 over 2 is 1. X, 2 minus 1 is just x, then 2. And we're going to look at the right side. 2x just becomes 2. And we're going to look at them at 3. Now from the left side, the gradient of 3 at 3 is 5. From the right side, the gradient at 3, well, is 2. 5 is not equal to 2, so you can't differentiate it at 3. Have we answered the question? Check. State the set of values for which the derivative is defined. So we haven't answered the question. The derivative exists for all values except for x equals 3. Part B, find the derivative for this set of values, or f dash x for this set of values. Well, we already have the top line, that's over there, and the bottom line, that's over there. So we can write the hybrid function. And notice that our domains for each section doesn't have the equal sign at 3 because we already established that there is no gradient at 3. Now we sketch the derivative function. So here we have x plus 2, and here we have 2. You can see there's a big gap there, that's why there's no derivative over there. Example 5, sketch the general shape of f dash x showing the points at which f dash x equals 0. So again, we've done this so many times, you should be good at this. So the gradient equals 0 at those points. And so the gradient is 0 at those points. Now the gradient is negative at that point, and it becomes, see, this is very steep, and then it becomes less and less negative. And as we go closer to that point, then we're becoming less negative as well. So the most negative will be at this point, and then these are all negative, but less than that point there. After this point, we can see that the gradient is becoming positive. And same with this side. After this point, we can see that it's becoming positive. What about this one? Well, we can calculate the gradient. So let's do this line here. We can see that it's 1 over 1, rise over run. So the gradient there is 1. And the gradient here, we drop 1 across 1, so it's -1. So -1, that one's 1, -1, 1, -1, 1. But notice that the intervals have open circles at each endpoint because we can't find the gradient at those points. Thank you for watching. You might want to give this a go one more time. Maybe pause. If you're on an iPad, you can screenshot and see if you can draw the same gradient. See you next time. Bye.